So I hope my screen is visible to you. Good morning. Today we'll be seeing transformers, which is one of the um, fundamental changes that were brought about for natural language processing, especially, and more for sequence to sequence. We'll be seeing transformers and variants of transformers for natural language processing. So let's get started. Let's have a quick recap. We saw that recurrent neural networks were used to model sequences, and LSTMs and bidirectional LSTMs then dominated the scene because they overcame the vanishing and exploding gradients problem. And sequence networks were designed, which brought in generalizability. So we could have um, language translation or video subtitling. Anything that was a sequence could be modeled using sequence. Then at the end of last class, we saw that attention is a mechanism that allows us to choose which parts of the input to see and pay attention and help in the translation. So this is what we saw up till now. We also saw convolutional neural networks, and there are some concepts of that as well that we will be using. So this is a very famous paper that came out sometime in 2017, I think, which is that attention is all you need. So this was proposed as an alternative to sequence, and it increased in computation speeds drastically. Now, if you remember, sequence to sequence consists of multiple RNN networks in an encoder decoder fashion. And RNNs typically in language would involve LSTMs that have three gates: the input gate, the output gate, and the forget gate, which involves a lot of parameters that need to be trained. Instead, transformers propose that all you need is a complex set of attention networks that can capture this behavior of sequence. Now, attention is simply weighted um, nodes in a multi-layer perceptron. So, computing that is far easier than computing all the hyperparameters required for the input, output, and forget gate for a single LSTM cell. And a sequence, we will have so many LSTM cells. So this was proposed by Google Research, and the following slides we'll be seeing is derived from the reading group of the particular paper. Attention is all you need. So first we need to understand why transformers were developed, what particular gap it is they were trying to fill in coming up with a new algorithm for sequence. At the end of the day, transformers are sequence networks. But what is it? What was the disadvantage of sequence that they are trying to overcome? So the first thing is the methods that we have seen till now, RNN, LSTM, GRN or GRU, they've been state of the art in sequence modeling problems. We know that RNN generate a hidden state function, which um, takes the previous hidden states as um, input. So that's how we got the sequence information, right? When we had a sequence of varying length, the hidden state information, which had the same weight, ensured that yes, we have some model of the sequence. But we already saw that um, that led to problems with exploding and vanishing gradients. But at a large scale, what it means is we have a lot of things to keep track of. Another thing is the model at a particular point is learning from a single sample. The sample itself is a sequence. Now, this prevents the network from learning in parallelization with the other training examples. So, we have a large corpus of sequences, but the model is learning only one sequence at a time while it is updating the weights. In transformers, instead, we have a mechanism to learn parallelly from different samples as well. Then, as we saw at the end of last class, attention mechanisms have become an integral part of sequence, but they were only used, as I said, with recurrent networks or sometimes even with convolutional networks. They have not been used with um, naive deep learning or naive neural network models. And this paper proposed that attention in itself is powerful enough so that we can throw away the RNN and CNNs, which are difficult to train. So, what does this mean? We are reducing the sequential. No, before we go into that, we saw in CNNs, we are seeing different parts of the input, but still we are not parallelizing the training samples. And in CNN, we saw a lot of ways the parameters were reduced. We saw max pooling, we saw different layers of convolution and max pooling that created a sort of compression. But in all of these methods, there is a problem that when in a sequence, when things are far apart, we are losing out on information because the hidden state has gone through so many layers of forgetting and other uh, things that long range dependencies are a problem even in RNNs or LSTMs. And in text, it is often very important to have long range dependencies. You might have a sentence in the beginning of a paragraph that suggests we are in this country. And maybe 20 sentences down the line, it says something like, hence, I took a flight back home. And then your question or your task might need you to connect the sentence in the beginning and some sentence 20 sentences down the line. So, transformers, the first motive it had is to take advantage of parallelization. The second is to use this complex set of attention to gain information for long range dependencies. So now, and the third, of course, is to simplify the model such that we are able to learn more with less information. So the problem structure right now here it's for translation where we have a set of input symbol representations and output. It's basically a sequence to sequence model input and output which we saw in detail last week. So this is how the architecture looks. This picture is taken from the paper which you can look it up. So what we are doing here is you can see the differences between sequence and this. In sequence to sequence, we had a set of LSTM units to which we gave the input to the encoder, and in the output as well has had a sequence of LSTMs which had the output sentence. Now here what we are doing is that the inputs are given. There is no notion of giving it in sequentially. We'll be seeing how the notion of sequence is captured by transformers at around the end of the talk. So the idea is that this part of the network is the encoder and this part of the network is the decoder. And finally, here we have the output probabilities. We'll be saying each layer of this network in detail, but we can have an overall view at the moment. So we have this input sentence and we have this input embeddings. As our previous discussions, input embedding can be pre-trained word vectors or we can train them as the transformer is being trained. Then we have something known as a positional encoding, which we'll be seeing later, which enforces a sense of sequence into the network. We then have n layers of this, which is basically here we have multi-head attention. We'll be looking at these terms in detail. And then a feed-forward network. This is quite similar in CNN how we had multiple layers which were then flattened into a feed-forward network. So this is the encoder part and this is carried on into the decoder. Now, the decoder here, the outputs are shifted, right? Similar to how in sequence we had time shifted the output. And then we learn from the decoder information as well as the encoder information and finally flatten it into a feed forward network. Then we have the um, output probabilities. I'm sure this sounds a bit complex at the moment, but we will break down each of these components so that it becomes clearer. So, in effect, we have an encoder, a decoder, we have a multi head attention layer, we have a feed forward network, positional encoding, and yeah, that's about it. Let's see how we move forward. So, of course, the entire paper is about attention. So, we will be seeing what kind of attention is being applied, how many ways of it are used. So, the first, we have three ways attention has been modeled. The first one is self attention in the encoder part. Then the second one is self attention in the decoder part. And the third is the encoder decoder attention. Now, whenever you see this word masking in deep learning, it is a way in which, if the masks are learned, it is a way in which we can have interpretability. So, in last class, when I mentioned about attention, we saw this metrics which learned the alignment problem, which was a sort of interpretability that this particular word in this language probably means the aligned word in another language. So these masks learn. So a mask is basically going to gate the input and output. It's going to tell you which places attention was successful and where it was not. So this helps us in the long run to know how the translation was done. I'm using the term translation because that's what this was primarily evaluated on. But this just reminding that this is a form of sequence network. So before we go on to the next concept, let's just revisit attention again for clarity. So we saw that attention were weights in the network. Here, let's go a little bit into detail as to how this attention weight is calculated. So mathematically, we say attention is a form of triple, where we have query, key, and value. And the softmax between the query and the key is the attention weight. Now, in sequence, query would be a word, and key would be a position in the sentence, and value would be the translated word. So the attention weight would be calculated based on the query and the position, and finally we'll get the value. So this kind of a dictionary approach of key and value or weight and value is what we will be seeing in this paper. It's exactly the same where we had a bunch of weights for positions, and here we formalize it by using the terms query and key. The key can be anything, it need not be exactly position or things like that. And just to keep everything differentiable and to have set of probabilities in this case, because it makes sense, we have a set of input nodes, we want to know which to pay more attention, and it is similar to saying to which we have more probability, and we have used the softmax for that. So now we come to scaled dot product attention, which is a part of the encoder and decoder networks. And as we saw before, there were three types of attention, and we will be looking into how this query key value is being used by transformers. So we have two kinds of attention, additive and dot product, and we will be using dot product attention in this. So in additive attention, what we do is that we have the query and the key, and we apply weights from the um, neural network perspective. So once we have weights and query and the key, we automatically would do what generally we do at the end of every layer, which is we apply an activation function and then apply a softmax on top of that. Now, this particular work on transformers revealed that why do we need to apply the same notion of weights to attention, whereas we can just directly do softmax between the query and the key, rather than sending it to neural network and then doing the activation function and then getting the probability. The query and key are in themselves complex enough that a direct softmax can give us a lot of information. Now, in the previous lecture, the sequence one I took, um, additive attention was used in the sense they were part of the training network. Now, here also they are part of the training network, but they are used differently. There are no weights here. We have the weight is obtained by simply the dot product between the query and the key. So this is one way in which transformers speed up the process of finding various attentions and various translations. So here in the figure, what we have is that the key and the query are multiplied, they're scaled, and the mask is optional. In fact, in the originally proposed version, the mask is only there in the decoder version. A mask is basically a binary vector like 100011. So it's going to help you understand which of these attention networks are successful for the data. And the softmax is going to give you a set of probabilities. And finally, with the value, we get the decoded value. So now we come to multi-head attention. I hope you realize that these kind of layers is what we saw in convolutional neural networks. And here, what we do is we instead of single dot product attention, we calculate multiple attentions. So what does this mean? This means we take the advantage of the entire training network and then in parallel um, do the scale dot product attention, and then we concatenate it, make it linear, that is we flatten it, and then send it on to the rest of the network. And we did the same thing in convolution networks. In convolution neural networks, we had a lot of layers. We did max polling on all those layers. We compressed it and then we flattened it and sent it to a feed forward neural network. The concept is exactly the same here. We have a lot of layers of the training samples and then we concatenate, flatten it, and send it on. So now, after this discussion on attention, we come back and see what are the various attention networks in the transformer. We have the encoder decoder attention, we have self attention in the encoder, and self attention in the decoder. Now, in the encoder decoder attention is kind of intuitive to understand because what we are doing is learning from the encoder and the decoder, which is suggesting we are learning the translation mechanism. Now, the self-attention layers in the encoder and decoder are learning how the sequence information is happening. So we saw various layers for the input. So we now mimic a kind of sequence by telling the previous layer and the next layer. So how does the data flow? We have the input. We split the input into various layers. We calculate the attention in the resulting matrices, and then we concatenate the result and get the final output. Now I'd like to take a special mention on self-attention in decoder. Now, we must remember in the decoder at inference time, we will not have access to the entire decoder input. Instead, we will have access only to whatever we have seen so far. So, in the decoder network, in the attention for decoder network, we can only access layers before it. So, if I am at the word soccer at decoding, I can only access the layers I and play and not the layers for in the morning. because, as we can imagine, in the morning is not going to be available at inference time. We also saw this in sequence in the form of teacher forcing, and the concept is exactly the same. Now, why did we use self attention? There are a few spelling mistakes here. I will correct that. So, the total computational complexity per layer reduces drastically. So, this is an explanation from the paper where we have that self attention is doing much less than recurrent or convolutional networks, and that was one of the first motivations of transformers. Now, not only should something be faster to compute, it should also have the same value, as in, it should bring to the table the efficacy in translation that we saw in recurrent or convolutional networks. And in this work, they proved that they have the state of the art measures for translation and other sequence tasks. And it's also much easier to obtain things between long range dependencies because, as I said before, the forget gate and the input gate and the output gate, which were introduced as safeguards for exploding and vanishing gradients, were um, also added in a layer of complexity that ensured that long range dependencies suffered. But here, due to less complexity and the fact that there's a parallelization, long range dependencies are handled in a much better way. So we saw the till now, whatever we saw for half the lecture was basically various ways of attention. So this is the self attention for the encoder, self attention for the decoder, and the input output, encoder decoder attention for the decoder. Now, these are normal feed forward networks and they're used in a very similar manner to convolutional neural networks where we flatten various layers and um, push it onto feed forward networks. So, now we come to this positional encoding. Now, in transformers, inputs are not given in a sequential format because there's no notion of sequence. There are just various layers that are there in parallel. And though we use terms like previous layer, next layer, it's not passed into the network in that particular way. So, to ensure that we have a sense of sequence for both the input and the output, we use something known as positional encoding. So, this is the formula for that, which basically says um, it has three functions. One is it brings out values between -1 and 1. Second thing is that it is talking about the position of a token. So it is a function of the position. And then it says that if it is even or odd, it shall follow a sine or a cos function. Now, what this is trying to do is basically give a differentiable format for position because you need to remember that um, in a neural network, when we have backpropagation um, and error estimation, unless it's differentiable, we are not able to learn the error surface. Now, so pos is the location of the word and I is the index of the dimension in the word embedding. So both are important. So we need to know which particular value of the vector we are referring to and which position of the sentence we are referring to. Now that we have a representation of that, we move on into the network. So this is the starting of the network, the positional encoding. So then, there are more details in why this particular format. So that you can see the paper. So this is the takeaway I wanted you to have. that it is differentiable, the values between minus 1 and 1, and it is a function of both the position in the sentence and the position in the vectorial space. So, how is the overall architecture? Now that we've seen most of the components of transformers, while decoding, we saw last class that we have beam search decoding and greedy search. In the transformer, the beam search decoding is preferred, and it's the state of the art in translation, and it's faster to compute, and it is interpretable by examining the attention weights and the masks. So, that's an added advantage. So let's pause here before I move to the next one. Any questions? Okay, so we will move into um, how transformers have generated other um, representations and architectures for language. Before we get into that, we'll first see Elmo, which is language model, and we'll see what are the advantages of this and how the combination of this and transformers led to another natural language processing architecture that has been very useful in the recent research space. So Elmo is explanation for deep contextualized word representations. I remember one student who asked me for two two words that occur in different contexts. Do we have two different vectors? And I had said, no matter what the word, we have a single vector, but the vector information will contain um, information between the existing meanings. So if I have a word that has two meanings, it will be close to words that have both the meanings. However, you can understand that when we use it as a lookup from pre-trained word vectors, we are going to use the same um, representation in both the ambiguous contexts. To address that, we came up with Elmo basically. So we replace static embeddings, which are obtained through lookup, with context dependent embeddings. So given the context, in this case, we will generate a new vector. Now, each token's representation is a function of the entire input sequence computed by deep bidirectional language model. So, because it is bidirectional, we saw the advantages of bidirection for context. So, because it is bidirectional, we have context, and for each token, we return a task dependent linear combination of its representation across layers. And different layers capture different information. Now, what this means is that in effect, we just had a simple lookup before that given a word, this is the vector. In this case, however, we have a entire trained model given to us where we will input the sentence and then get the corresponding vectorial representation for the word. So now we can't just have a large text file where we can just take the word and its corresponding vectorial representation. Now we need to run it on a trained neural network. Of course, training it is the hard part, and if through this pre-trained neural network, we'll get the context and the uh, different vectorial representations for the same word. And context is achieved by using a bidirectional language model. So the idea is that we train a multi-layer bidirectional language model with character convolutions on raw text. So each layer of this language model computes a vector representation for each token. And then you freeze the parameters of the language model. Then on top of that, depending on what task you have, you can do the softmax weights for classification and any of the tasks. And then you combine these layer wise representations. So either you can directly just use these vectorial representations into a new model, or you can learn it together with the model, because anyway we have frozen the parameters of the language model. In effect they are the same whether you model them together or whether you model them separately, because we don't allow the parameters of the language model to change that has been trained on a far larger data set. So the idea is that instead of just having a lookup, we now have an entire deep learning architecture at your disposal to get different representations. So we have a forward language model, we have a backward language model, and they are trained jointly for the token representations. Now, as I mentioned before, the input token is completely character based. And then we have a convolutional neural network to further reduce the dimensionality. And the advantage of using character embedding is we'll not see a lot of unknown tokens if it's not there in the dictionary. Of course, it's much harder to evaluate, but with more data, Elmo showed how it is more powerful than normal lookup word embeddings. So it can be used as additional input, it can be tuned with dropout, and so on and so forth. So the idea, the key takeaway I want you to have is that instead of having word lookup, we now have an entire pre-trained neural network that is going to generate our embeddings. So now we come to BERT. BERT is the combination of these two ideas, where we have a transformer that is already very efficient to compute sequence to sequence. And then we have this idea that embeddings will depend on context. So we have a pre-trained network. So what BERT does is that it gets this contextualized embeddings from a transformer, because most language does anyway involve a lot of sequence, and now we have this complex architecture of a transformer available to us for further processing. So BERT is bidirectional encoder representation from transformers. So here we have a sequence of transformers, and in Elmo we had two bidirectional we had two LSTM models, one of which was in one direction and the other was in another direction. So this is a difference between the two. This is taken from the Bird paper. And what we have is that uh, instead of LSTMs, we have transformers here. That is the key difference. And we use this network in exactly the same way we use Elmo, where you will give the input, you'll freeze these weights, and then pass it on to further processing. So right now, BERT is dominating the language modeling space uh, as long as there is enough data. So to give an example, we have the input, we have token embeddings, segment embeddings, and position embeddings. Here we don't use the position encoding, but we have position embeddings that are also learned. So as with any transformer, we need to address this sequence problem on how we can move ahead with it. So we have generative pre-trained transformers, which is between these two actually, Elmo and BERT. And the idea is that instead of, it is a generative model. Every time you use the word generative, it means it's not just for classification or just for clustering or whatever the task it is. It is not modeling the mm, task, rather it is modeling the data. So we say like language model is a generative model. We saw that given a word we want to predict the next word, or we want to predict the context, so that is a generative model. So here what we have is, in a transformer with one encoder we have multiple decoders, so that gives us a way to create a language model. And this There is a lot of, whenever you talk about NLP, you'll hear the terms GPT-3 or DAL-E, because what GPT-3 did was compute a huge, deep network, and which were pre-trained and then given to um, coders for further processing. And there was an explosion of articles. For example, in the Guardian, there was an article which said, this has been written by a robo, and I am a robo, and this is how I understand language, and so on and so forth. Always take such information with a pinch of salt, because if you read the fine print in the Guardian article, it will say that the model generated 8 responses, and we edited it and made it look seamless. So yes, all these networks have brought natural language processing to a much greater and more applicable format. But the idea is that all these ways, all of which what we are training, it's still not giving us a so-called perfect model of language, because first of all, language keeps evolving. And the second idea is that how are you going to incorporate a lot of the knowledge we have into the language? Right now, what we are doing is leveraging the fact that similar words appear in similar contexts. But there's also this notion of deeper meanings of words and context and nuances, which um, may not be captured without um, domain knowledge or common sense knowledge, and so on and so forth. Dali, which is a play on Wally and the painter Dali, gives us interesting things on generating images based on text. Now, as you can imagine, that's also like sort of like sequence, because image we cannot exactly call a sequence, but there's also used transformers. So the to recap, what I want to say is that transformers used only attention. They modeled sequence, but they did not use the complex parameters of RNNs or CNNs and things like that. So they started computing things very fast. Also, they showed that they were performing even better than the complex models such as RNNs and CNNs. And that is because of the way they have utilized attention in various layers and leveraged them. So that was transformer as it is. Then we saw that embeddings have moved from simple lookup to having pre-trained models themselves, so that we can move on to having different vectorial representations where ambiguity and context is dependent. So from there, we saw the BERT network, which has a lot of information for natural language processing. And then I just discussed a few of the happening things that appear in news now and then, so that you can have an idea what's happening. And do look at this link. And especially, I wanted to look at a very interesting example, which is about arranging blocks. And you will see that it has a close resemblance to the input, but ideas that blocks stacked one on top of the other often involve a lot of information on space, which may be missed if you're only looking at language, and that is why domain knowledge is important. So yes, thank you.